Had a good lunch? Full? Feeling sleepy? Okay. Uh, okay, no problem. Just a quick show of hands, right? How many of you are ML engineers or have worked across some of these projects, or want to get to ML, maybe? Yeah. Great. Any DevOps engineer here? People who work on cloud, Kubernetes, deploying like software products. Okay. So about me, I started as an ML engineer, a data scientist, but over the time I realized, okay, we all can build models, but the meatier part is where you get to deploy it, right? Where you get to scale it to users, get your ML products to users who can actually use them and realize value in their daily lives, right? Uh, right now I work at a startup called Navatech where we build this LLM solutions for daily wage workers, so that make sure that they go back to their homes safe, right? Ensuring their health and safety. Before that, I worked at Google and Amazon as an AI architect and some of these roles. So these are some of my experiences across the years collated together into a deck that show you some of the things which worked for me, right, while I was deploying some of these models out. Okay, okay. Okay. We all might have seen this, right? The rise of LLMs, I think, somewhere around 2017, where the first attention is all you need model came in that changed the entire ecosystem, right? And from there, this journey has been quite altering, right? Today, we have a lot of top tier models like GPT, Llama, Google Palm, a lot of others, but it all started with just a very small paper we showed or which made us understand how model can pick specific parts of your input and give more attention to it and generate an output after that, right? Yeah. I'll share some guidelines on how do you start with an ML solution, or specifically an LLM solution, right? So what are the things you consider when you want to decide what is the model that you would want to pick up to build a solution? I think start with, yeah, so start with the first basic question, do you really need an LLM? Right, and we tend to miss this a lot, right? We try to force fit ML solutions, these LLM solutions into every wild dream that our business owners comes in, right? But first you should ask, starting with, do you really need an LLM model, right? That could be, your idea doesn't require LLM, or it can be simple enough that can be solved with some rule-based applications, right? But if you still want an LLM, then okay, first step is great. Okay, I need to use an LLM. Second, you decide what you want to use, right? Is your need covered by a lot of these pre-trained models which are available like Llama, Falcon, or GPT models, right? 95% of your use cases they'll see every day will be covered by this, right? But there are some niche use cases. So let's say you want to answer a specific healthcare related question, right? Or maybe you want to generate something which is very niche to a financial industry, or maybe some government product that uses some specific intelligence, and those open source or already trained model might not have that information, right? A good way to go is RAG, but still if you want to do it, then okay, you now know you want an LLM, okay, this is the LLM I'm going to use. Second or third thing that you should consider is what is your accuracy requirement, right? Is it a mission critical?
Excuse me, Jonas.
Yeah.
So we have a little bit issue with this.
Okay.
Can we move the laptop over here, like real
yeah,
quick?
you can do that. You can do
All right.
that.
Thank you.
This will still work, right? Yeah. Sorry about that. In the meanwhile, maybe anyone want to share any of your experiences using these ML solutions, or anyone use ChatGPT? One, it's don't hide. I know everyone use ChatGPT, right? Most of us use even to write our codes. So yeah, what is your experience with ChatGPT? Does it hallucinate a lot? Yes. Okay. And have you tried or thought about, okay, what it takes to me to build a ChatGPT like solution, right? Maybe my company or some of my customers wants to build it. Maybe a thought process around how should I go about building something similar, right? Okay, we are back. So that's some of these things we'll cover. Third question you should ask is, what is your accuracy requirement, right? Is it something very mission critical where you need point blank answers for every question, right? You don't afford to get wrong, right? Where you need bigger LLMs, right? Like GPT-4, Llama, Falcon 180B, which are large models, and by research we know that larger models means larger capabilities, and that accuracy of those models would be good. But there could be niche use cases, right? Let's say you are building a app for a farmer in a remote part of Thailand who uses these LLMs to maybe get answers to related to his crops, right? You can just use a small LLM, deploy in its phone, and he can still use it. Right? You don't want that model to write French poetry for him, right? You can still use a very small LLM like Mistral or Falcon 7B, who still works and give him the right results. Yeah. Yeah. Then another question you should ask is, how much is your financial investment you are ready to make, right? Things like, do you really want to, coming back to your these two questions, right? If you want to fine tune a model, that it's going to be costly, right? By some experiments that have happened over the industry, we know that to train a LLM with 1.5 million tokens, and to get it to a good accuracy, you need $1 million, right? So that's a pretty big financial investment that you have to make. So you have to also decide, okay, I might be better off just using a slightly lower accurate open source or fine-tuned model, or already trained model, and not use or spend that $1 million into training a new model for me, right? And then purpose and licensing, right? So if you are, let's say, using models like Falcon, they also have some restriction around what you can use them for, what you cannot, right? Similarly with GPT, Gemini, this. So you also have to figure out, does something that you are building is covered by the licensing aspects of these models? Are you allowed to use that or not? Okay, now let's say you, with covering all of these questions, you decided, okay, this is the model that I'm gonna go, right? I'll use Falcon 7B, or I'll use Llama model to deploy and then use in my application, right? Deploying is not easy, right? And while it was still harder for deploying classical ML models, the complexity increased when we started figuring out or talking around how now you have to deploy these large meteor models who are power hungry, right? Who are GPU hungry. The more GPU you give them, they'll eat a lot of them, right? So there are some of these things that you should consider, right? Or the challenges which are there is around computational resources, right? These days, there is a scarcity of GPUs, right? 800 GPUs are not readily available. So which means that your models which are compute intensive, which are, and these are not CPU bound, but these are memory IO bound on the GPU itself, right? So you need more compute in terms of GPU to run these models. Scalability is an issue, right? It is not, as I'm not say simple, but it is not equivalent as scaling as a traditional software application. But scaling a GPU bound application is hard, right? Because first, getting that GPU, making sure that your application is balanced across all of these nodes and all of that thing, right? Third is latency, right? Latency is a big issue. All of us have faced a problem where a software product we build, and the answer is it's not fast enough, right? You need to optimize it. You need to fast enough. Before ChatGPT, or let's say early 2021, we were trying to optimize and make solutions faster and faster, right? But now suddenly with ChatGPT and the rise of LLMs, we are okay with the user waiting for a couple of seconds, right? We expect user to wait a couple of seconds for us to give a response back to him, right? And you still want to minimize that, right? You don't want the user to maybe wait for 10 seconds, right? For example, if you deploy a Llama model or Falcon model in a vanilla instance, it will take up to 10 seconds for to generate just one response, right? You don't want the user to wait for 10 seconds. There are some clever tricks, our friends at UI UX has done, things like streaming, right? So you don't want the model to generate everything and give to user, but send the token as they are being generated, right? That way user is busy, right? He is reading in the parallel, you are generating tokens and you're getting him, right? So he's not waiting for you to generate the entire response, but what ChatGPT does is it streams, it shows you, start showing token by token, right? So you get busy on reading them. Model sizes, right? While in the previous, topic around how do you decide a model, I talked about decide a model large enough, which covers a lot of your use cases, but this is also a problem, right? Larger models means high latency, high memory requirement, high compute requirement, scalability is hard, right? So you need to find a balance between, a lot of these things, right? Here comes, I think, to cover both of these aspects of how do you now manage these models in production is where we started evolving with. First there was DevOps, then we came to MLOps, where we talked about using tools like, Vertex AI, AML, Amazon SageMaker, or open source tools like Qflow to give you a platform to manage these models, right, or the life cycle of the models. But now in LLMs, we just not deploy the ML model itself, right? We are also deploying a packaged application. Things like a common use case with RAG or LLMs model is a RAG application, right? Retrieval augmented generation, right? So it's a packaged application that takes care of system message, what you want a model to do. There are parameters that you want to play around with the model and the entire orchestration around it, right? So if I have to cover this, I think DevOps is the larger world where we still decide. But then there is a small niche subset of DevOps is what MLOps is, right? I know it's and these days, if you see in the industry, there's a new role that is opened up in the AI world, right? It's called an ML engineer. It's not what you think, right? ML engineer is not someone who builds an ML model, but ML engineer is a mix of a software engineer plus a DevOps engineer who helps the data scientists to deploy this model and scale them up, right? So this is a very niche role for that, right? Who a dedicated person or a skill that manages, once the model is deployed, he takes care of scaling it and getting it out. So now we know how do you decide a model. We know challenges on deploying that model. I think now here Kubernetes comes as a rescue, right? There are a lot of neat features that inherently Kubernetes has that we can use and make deploying of these models smoother and a good experience for the user, right? Start with container orchestration, right? I assume people here know what are containers and these things, right? So you can still package your models as containers, and then you can give it to a platform like Qflow to manage that container orchestration, right? The problem there is, yes, you can leverage container orchestration, but still these are very large instances, right? These are very large pods. Managing them is still a problem, especially with GPUs. We know that a lot of these models don't like to share memory, right? They don't like to share the GPUs among other models. So how do you manage that? Then with Kubernetes comes with auto healing or high availability, because internally it can manage if there are some pods which are going down. If there are high latency, it can spin up pods. It can pull them down. A lot of these things, right? There is multi-cloud deployment. Let's say your organization also wants to, your whole infra is in maybe AWS, but you got these large GPUs on let's say Azure, right? You can still with Kubernetes have a multi-cloud deployment where your overall application sits on AWS, but your ML workloads are on Azure, right? Because you got your GPUs there. Kubernetes inherently will help you also with resource efficiency, making sure that you get every penny out of the investment you made on making or provisioning that cluster with that cloud provider. Yeah, good, right? And this is something that I have seen when I pitch into my team or some of my customers that, okay, now you need to, or tell the data science team that, okay, now take this model, deploy this in a Kubernetes cluster, right? This is the responses, right? Because they think, now I need to learn DevOps, I need to learn Kubernetes, and it's an additional learning curve for them, right? And we as a data scientist, we are still happy with our Jupyter notebooks, right? We don't want to come out of that, right? We create a notebook where everything works, give it to, like, it's your problem now, right? I have done my work, right? But this is where this comes in, right? And that is where I try to look beyond and evolve out of just building model to onto a world where I figure out how to deploy them and making sure that these models work for my users. First tool that you have as an ML engineer in the MLOps world is Kaito, right? It's an abbreviation for Kubernetes AI Toolchain Operator. It's nothing but it enables you to write a custom container resource definition, right? CRD. So what you do is you package your ML model as a container, give the specification, okay, this model needs this much memory, right? A rule of thumb is you just double the amount of parameters you have, right? Let's say Falcon 7B, you need 14 GB memory, right? Same if you now talk about, let's say, Falcon 180B, right? That's 360 GB of memory that you need to run that model, right? That's a very big cluster. And it's simply because each parameter is a floating point, so you need 2 bytes to store that. So that's why double. Plus, you also need some additional things, right? We'll talk about some of these things, but rule of thumb is how many parameters are there? Just double it by 2, and you have a requirement of how much memory you need for that model. Then there are, an intelligent thing that Kaito does is it auto provisions these nodes for you, right? So it calculates, okay, for this model, this is the amount of compute I need, and it will auto provision it for you, right? So you don't have to be in that guessing game of trying out multiple instances, figuring it out. This is the right instance for me, right? So you don't have to do that, right? It manages that, and the benefit of this comes in where you have a lot of intermittent traffic coming in, right? You don't want to have that large instance always being occupied, right? Versus when the traffic comes in, Kaito knows, okay, for this model, this is the amount of compute I need, and based on the seasonality of this traffic, it can orchestrate and have those compute available when it expects the request to come in versus having it running always. Third thing that it does is it also allows you to do GPU sharing, right? The same GPU can now run multiple models in parallel versus one model occupying one GPU, right? So you have a lot of memory or compute being wasted because earlier we were not able to share these GPUs across multiple models. And this is how it works, right? So you have the CRD that you write, a resource definition that you write for your model. I actually wanted to show you how to do that, but then my laptop was not being connected because of some issue, right? And in the workspace controller, what it does, it reconciles that CRD, right? It figures out, okay, this is the amount of compute I need. It then triggers the auto provisioning in the or the node provisioner, right? So what it does is it then takes the CRD that you write and uses another tool called Carpenter to interact with the workspace controller, integrate with your cloud provider like Azure, and then add new GPUs to the node as they are being requested, right? So it manages the entire operation, and your containers are now stored in private or public registry. It creates those GPU nodes, spins them up, and now you are able to serve all the traffic out. So I just wanted to show you the steps. Maybe in the end of the slide, I'll give you these resources out so you can go back and try it out yourself, right? So start with creating a workload identity, or first create a cluster, create an identity, assign that identity. Then there are these pre-written Helm charts, right? So you don't have to even write this Helm chart. You just apply, and okay, and you are good to go, right? You are good to now deploy these models using Kaito, which does a lot of these good things for you, right? But that's not enough, right? That's only on managing the infra, right? Now you have a managed infra. Let's say you can now manage your GPU nodes. You can manage your infra provisioning, sharing, a lot of these things, right? The next what I'm going to talk about is now how do you actually optimize your model workload itself, right? So there are two parts to the story, right? Optimize your infra, optimize your model itself, right? So we have talked about, okay, this is how we optimize your infra. Second is how do you optimize your code itself, right? Second tool that you have is VLLMs, right? VLLM, what it does, it's a high throughput, memory efficient framework, I'd say, to help you accelerate that, right? And it does, it leverages some neat algorithms like page retention, I'll talk about that, continuous batching, and then it is optimized for CUDA kernels, quantization, so you can actually shrink your model down in lower precision and then still run them, right? A simple example of people know what quantization is? Show of hands, please. Anyone knows what's quantization? Okay. Just to simplify, right? Let's say the model is trained on floating points, right? For example, each node in that model is floating point, right? If you want to quantize, just remove the int, or just remove the floating point and have an int, right? So because you are removing the floating point value, let's say 1.01, right? If you multiply it by 1.01, you will get some value, right? Versus if you multiply just 1 multiplied by 1, you'll just get 1, right? So you are losing some precision, right? Because you are removing the floating point. So that is much performance drop that you can, or accuracy drop in the model you can expect. But there are even more algorithms that even helps you to compensate for that, right? So you have quantization, and then it seamlessly integrates with Hugging Face, right? So you can use VLLM to deploy any open source model which is there in Hugging Face registry, right? So you don't have to do any extra work for that. There's a list of currently available models, but it is fast growing, right? Yeah, it can be a bit small for people at the back to see, but I'll share you the deck or the links, like you can refer them later. First tool that we have in our belt is continuous batching, right? Before that, just a primer on how LLM works, right? So you give a prompt in the ChatGPT, you write me a code to add two numbers, right? So that your prompt, right? Now these yellow boxes are your prompt, the words that you have written, and then the model starts generating these blue tokens, right? The next following words that it has to answer you, and then it starts with that red, right? So model or token generation or an output is iterative. You generate one token by one, right? So you are not actually generating the entire sentence is in one go, versus you are just predicting. At core, these LLMs are just next word predictor, right? They are just as good as your Gboard that you have your phone, right? Which predicts what is the next word you're going to write. It does the same thing. It's more trained on a larger set. It knows more things about the world, versus that Gboard just knows about you. It's auto-regressive, so it consumes then back the previous words and then gets to the next, right? It again, so first 3 tokens it will generate the fourth, and then take the four tokens again as an input, and then generate the fifth, right? And it goes by that. And then completion is, yes, like decided by the model, right? Your next tokens are decided by model. It knows, when to end it, and at the end you can actually ask the model to give a specific token at the end, so that you know, okay, this is end, right? The generation has ended, and you can now proceed further. With that, first is this is static batching, right? This is how currently or previous to when we were introduced to continuous batching, this is how it used to work, right? So you got the S1, these 3 tokens, you generated 2 tokens, and then you ended, right? If you see here, if I say I can accommodate 8 bits in one batch, I'm wasting 2 bits there, right? Last 2 bits after end. Second, for S3, I'm again wasting 3 bits. For S4, I'm wasting 1 bit, right? Versus what continuous batching does is, you actually start right from where the previous ended, right? So you continuously keep on utilizing, right? So versus if you see static batching, you are wasting almost 6 bits, versus in continuous batching, you are still utilizing them, right? So it gives you that memory efficiency, right? It gives you every penny out of that instance that you have invested in, right? And this is just a basic explanation of continuous batching, but if you want to read more how actually it works, you can read that, right? So it dynamically recreates batches, right? So let's say if knows I have 2 bits left, it just create that batch, use that, and then move to the next, right? Instead of wasting it and starting from scratch again, starting from 0 and occupying the same instance. Let's say 8 bits memory again, right? Fills GPU capacity for each token, so you are filling every available space in that GPU and getting your tokens out of it. And a good practice is if your token sizes or inputs are varying. Let's say in ChatGPT, I might write, give me a program to add 2 numbers in Python. Maybe my friend will write Python add 2 numbers function, right? Something like that, right? So when with these variances, it becomes even more efficient with continuous batching, right? Because the tokens are varying, the wastage is high, and then but you are continuously trying to optimize that wastage, and you are trying to fit everything together, right? Next, I talked about is paged attention, right? So first, what it does is before any inference, right, any prompt, before even the model starts to generate, it builds something called as a query and a key for that, right? So input and output pairs, right? What we called as a KV cache. Now this KV cache is used for the model, or it creates that attention mechanism. Now uses that to generate next words. Earlier, what we used to do was that it happens in a continuous block, right? We used to store similar to continuous batching. We used to store in a continuous batch versus with paged attention, what you do is you can now basically break them into smaller batches and then store them similar to how we manage OS's virtual memory, right? So you fill them wherever you have space available in that memory instead of waiting for an entire, let's say, artificial intelligence is the future of technology. That's an 7-word or 7-token length, right? If you don't have a 7-token continuous memory available, you might have to wait till that is available versus you just broke it into 4 batches of 4 and you stored one where you had 4 bits available and next you stored, right? So that way you optimize even and paste, because you now use a lookup table to figure out, okay, this batch is here and the second continuous part of this batch is here, and you quickly look them up and then use, right? Now, because you are using lookup tables here, what it additionally gives you is that now you can also parallelize this, right? 2 models can still use the same KV cache because there's a lookup table attached to this, right? So, there's something called as an parallel sampling. So with parallel sampling, you actually leverage KV cache with tokens and multiple models or multiple instances can still call the same cache at the same time. Yeah, so calling using VLLMs, yeah, in at core, it looks a lot of things that you might have to implement and it looks scary, but it's not, right? Everything is built right away for you. What you do is from VLLM import LLM, same LangChain orchestrator. What you do is create the construct LLM and give the Hugging Face ID of that model, right? Meta Llama / Meta 27F. So now it does internally calls that LLM, downloads it, quantizes it, and then uses continuous batching, paged attention, a lot of these things for you to now increase the performance. Same, it is very similar to the same OpenAI specifications, right? So you don't have to change a lot of things with if you deploy the model with VLLM, you can directly start using it with this construct. So this is the LLM serving stack, right? So at the core you have Kubernetes, which orchestrates everything. At top you have VLLM. There's also Tritron and DeepSpeed. I'll not talk about that, but you can go about and read. There's Racer, which allows you to then deploy or leverages VLLM Tritron to deploy these models out. And at the top you have a lot of these tooling available that even allows you to orchestrate and run multiple models at the same time. Yeah, so this is an anatomy of how a fine-tuned model works, right? So let's say all things that we do in step 1, step 2 was to, if you just pick a model out from the world and deploy, right? Now let's assume you want to fine-tune a model and deploy, right? How that works out. So first, when a user query comes in, that orange bar is input or KV cache attention we talked about, right? Then you the third one, right? That's the base model, right? So you load that, and then there's adapter weight, right? So the weights that your model trained on your data. And then you scale it up in your production pod, right? It looks simple, but imagine if something like this, right? One user came in, you provision that. Second user came in, you provision that. Or let's say even these are two different models, right? Right, and this can go long, right? This can go along as many multiple models you have, right? Imagine you have 50 models to deploy, or even 10 models to deploy. You might have to create 10 exact copies of the same deployment pipeline, right? Versus, and if you see here, there's a lot of wastage, right? If you see this, like till here, with till model weights, it's all common, right? Till model weights, everything is common. What only changes is this, right? The train model weights. So what you do is with LoRax, right? So third is LoRax, which is basically an optimization on top of LoRa. So what you do is it uses, again, the shared set of memory or GPU that we talked about in the first step, right? So it uses that. And it uses one base model weights. And for every adapter, you create as many weights as you can, right? And in inference, what you do is you ask all of them to infer, but you only use a mask, right? So let's say you want to use the output of model one and not the others. You use these marks to only add those and then get the final output out, right? So it's a very naive explanation of this. And then there's something called as dynamic adapter loading. Yeah, so what you do is same, right? So now, since there could be multiple adapter layers for all of your models, you don't want to even have everything in the memory if you're not getting requests for everything, right? So what LoRax does it uses dynamic adapter loading to figure out, okay, I can get a query for this model, so let me load that, and it has a tiering strategy on caches. Something will be on immediate cache, something would be on on, let's say, persistent drive, and something would be on offloaded to some cloud storage, right? So if you need that, then you can load them. Yeah, so it's just a guideline. Instead of doing this, I think a good way to this is leveraging LoRax, leveraging VLLMs, all of these to implement something like this, right? Where you use LLMs at the core to optimize the model itself. You use LoRax on top of that to figure out how do you orchestrate everything, and then you also use Kaito to even manage your infra, right? And all of these in combination looks, and this is a benchmark on LoRax, right? So this is your basically break even, right? So with, let's say, 25 GPU, this is the amount of compute that you can expect. This is the amount of token you can expect. But with LoRax, this is what you achieve, right? So it's almost 250x, right? It starts to degrade over time, but then you'll not have, ideally you'll not have 125 models being deployed at the same time, right? So for smaller chunk of model, which very high throughput, which very high users, you'll see a lot of, or a high gap between using dedicated instance versus using something like LoRax. To sum everything up, this is how your overall architecture will look like. So at the core, you have this LLM services deployed or used to deploy every models. Then you have a Kubernetes API server which manages everything and which allows you to talk to every model whenever you want, right? And at the top of you have a RAG application or database, everything which then leverages this model to generate the outputs out. This is one point where I wanted to show you a demo, but I'll share you the code. So first what we did was we created this with only one node and started deploying more models. Kaito got triggered. It figured out, okay, this instance I need 2 instances. So you can see here, it just scaled up, or it started creating more. It failed scheduling because containers were not available, and it started using, triggering more instances, creating more instances, and started deploying that model out. And this is a benchmark on if you combine everything, right? With continuous batching in VLLM, right? If you see, you get at least 2x to around almost 23x performance if you compare a naive model deployed in one instance versus everything summed up in and deployed, right? So I think I have shared all the tools that you have available in your belt to deploy your models now. Again, this is a benchmark versus Hugging Face pipelines. You can still see continuous batching exceeds a lot of, beats a lot of these available strategies that we have today by a huge margin. That's all. That's all. Thank you for having me.
All right. Have anyone have any question for Joinal here? Any hand?
No questions?
All right, no questions.
Uh,
Thank you.
Just these are these links if you want to go and read through them. And I know these links would be hard, so there is this QR code. Go scan this, you will get access to the link, access to the deck and everything, right? If you still have question, we can connect on LinkedIn, or you have my email, shoot me an email, I'll be happy to help. Thank you.
All right. Thank you so much.